Pluto, once considered a distant and puzzling minor planet, was originally classified as a member of our solar system's planet group. However, groundbreaking revelations from prominent astrophysicists such as Neil deGrasse Tyson and Michio Kaku have thrust Pluto back into the spotlight. They shared a surprising theory suggesting that Pluto could be on a collision course with Neptune. But how is this possible, and what could the consequences of such a cosmic collision be? Are we witnessing a rare cosmic event, or is there something more to this impending catastrophe? Join us as we explore the potential outcomes of a Pluto-Neptune collision. Once regarded as a full-fledged planet, but later demoted to a dwarf planet due to its peculiar orbit, Pluto remains an object of intense interest and study in the scientific community. Recent forecasts from leading researchers indicate that Pluto's orbit is dangerously close to Neptune's, prompting astrophysicists Neil deGrasse Tyson and Michio Kaku to raise alarms about the potential for a catastrophic collision between these two celestial bodies, a scenario that could pose a significant threat to Earth. But how can this even be possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system, taking an astonishing 248 years to complete a single orbit. Since its discovery in 1930, it has yet to finish even one complete revolution. Yet Pluto's orbital eccentricity doesn't end there. Its orbit is highly elliptical, starkly contrasting with the nearly circular paths of the other planets. Adding another layer of peculiarity is the angle of inclination of Pluto's orbit, calculated to be 17 degrees to the ecliptic plane. This means Pluto's path is much steeper compared to that of the other planets. The combination of eccentricity and steep inclination makes Pluto's orbit a complex puzzle. Perhaps the most intriguing aspect of Pluto's orbit is its interaction with Neptune's. For approximately 20 years in each orbit, Pluto comes closer to the Sun than Neptune. This contradicts what we might expect from their relative positions in the solar system. The answer lies in the gravitational influence of other planets. Pluto's unique orbital behavior was first examined shortly after its discovery. Astronomers were initially puzzled by its unusual trajectory. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's path is tilted and elliptical. The mystery deepened when it was realized that Pluto's orbit does indeed cross Neptune's path. The fact that Pluto's orbit remains stable despite these apparent conflicts demonstrates the intricacies of celestial mechanics. The study of this phenomenon involves the three-body problem, which seeks to understand the gravitational interactions between three bodies in space, such as Pluto, Neptune, and the Sun. This is akin to predicting the movements of these bodies based on their starting positions and the gravitational forces they exert on one another. In Pluto's case, this issue highlights how Pluto's orbit, Neptune's path, and the Sun's gravity work together in a complex manner. Terms like asymptotic libration, scope libration, and the VSK oscillation help explain this. Astrophysicists have determined that the phenomenon of libration is crucial in maintaining orbital stability between Pluto and Neptune. Libration ensures that when Pluto crosses Neptune's orbit, their relative positions are always at least 90 degrees apart, preventing a collision. Scope libration describes the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other large planet, it is positioned above their orbital plane, offering additional protection from a potential impact. Another key factor in maintaining Pluto's stability is the VSK oscillation, named after researchers V. Apple, LV, and Key, who studied the gravitational effects between three objects in space. This concept explains how Pluto's, Neptune's, and the Sun's gravitational interactions influence Pluto's orbit. The VSK oscillation helps us understand why Pluto's path around the Sun is so unusual. Despite appearing chaotic, it actually helps maintain Pluto's orbit for an incredibly long period. This oscillation shows that even in seemingly chaotic systems, there are underlying patterns that help maintain stability. All these components, libration, scope libration, and the VSK oscillation, help ensure that Pluto's orbit remains stable, preventing a collision with Neptune. This interplay of forces demonstrates how complex celestial mechanics can stabilize even the most seemingly erratic paths. Understanding the three-body problem is essential for unraveling the dynamics of these orbits, not just for Pluto but also for other distant objects in our solar system. Mathematical simulations from the late 1980s revealed that while Pluto's orbit is stable for now, it does exhibit minor variations that could lead to significant changes over millions of years. These simulations also demonstrated how the gravitational forces of giant planets like Neptune, Jupiter, and Saturn contribute to stabilizing Pluto's path. In fact, Pluto has a unique relationship with Neptune, where Pluto completes 2 orbits around the Sun for every 3 orbits Neptune makes. This orbital resonance helps maintain the stability of Pluto's orbit. However, Neptune isn't the only planet influencing Pluto's path. Jupiter, with its massive gravitational pull, also plays a vital role in protecting Pluto's orbit. Saturn's influence further contributes to this cosmic stability. Simulations indicate that Jupiter alone has enough gravitational force to keep Pluto's orbit steady over incredibly long timescales, possibly billions of years. It's as though Neptune, Jupiter, and Saturn are working together to prevent Pluto from encountering any dangers in space. These gravitational interactions are crucial for maintaining the overall stability of the solar system, preventing chaos that could arise from bodies like Pluto colliding with others or being ejected from their orbits. The importance of these gravitational forces extends beyond just Pluto and Neptune. The study of these interactions sheds light on the larger cosmic order, showing how even the most minor forces can have far-reaching consequences on the stability and motion of celestial bodies. Without these stabilizing forces, the solar system would likely be a much more tumultuous place. Objects like Pluto could collide with other planets or be cast out of their orbits, leading to unpredictable consequences for other bodies in the solar system. Tyson, a well-known astrophysicist famous for his role in the reclassification of Pluto as a dwarf planet, continues to evolve his views on Pluto's orbital dynamics as new information becomes available. Tyson argues that the renaming of Pluto was not a downgrade, but a necessary adjustment as our understanding of the solar system has grown. He sees Pluto's strange orbit and interactions with Neptune through a lens of continuous scientific discovery, recognizing the inherent unpredictability of space. While Pluto's orbit is stable at present, Tyson acknowledges that future shifts in gravitational forces, whether from the Sun, other planets, or unknown influences, could lead to unexpected changes. This uncertainty serves as a reminder that even systems that seem stable today are subject to change. Tyson's warning about the possibility of a Pluto-Neptune collision highlights the evolving nature of our understanding of celestial mechanics. While such a collision may not happen for billions of years, it underscores the importance of ongoing research and adapting our models as new discoveries are made. The study of Pluto's orbit is essential for understanding the broader forces that govern the solar system. Tyson's emphasis on the uncertainties of the future calls for continued observation and study, allowing scientists to refine our understanding of how gravitational forces and interactions shape the destiny of planets and dwarf planets alike. As we continue to study Pluto's path and its future potential for change, we are reminded of the unpredictable nature of space. Despite the current stability of Pluto's orbit, its future remains uncertain, and the possibility of a collision with Neptune or even a dramatic shift in its trajectory remains a distant yet fascinating consideration. As we learn more about Pluto, our solar system, and the universe itself, we will continue to refine our understanding of how celestial mechanics influence the paths of the planets and dwarf planets within our cosmic neighborhood. Pluto's future may still seem uncertain, but with each new study we gain deeper insights into how our solar system operates. The delicate cosmic dance between planets such as Neptune and Pluto emphasizes the sheer complexity and wonder of the universe. Even though Pluto's orbit may remain steady for the foreseeable future, there is always the possibility of change hidden within the chaotic forces of space. Pluto's path through the cosmos is far from simple. Despite its current stability as a dwarf planet, it offers a remarkable example of the intricacies of celestial mechanics and the forces that govern the movements of bodies in the solar system. The fact that Pluto's orbit intersects with Neptune's without causing a catastrophic collision challenges our traditional expectations. This curious case invites further investigation into how different forces cooperate to prevent space objects from crashing into one another. While Neptune's gravity is often regarded as a primary influence on Pluto's orbit, the interactions with all the solar system's planets, particularly the massive gas giants, play a critical role in stabilizing Pluto's path. Jupiter, with its immense gravitational pull, plays a pivotal role in this gravitational interaction, helping to maintain the stability of the smaller and more erratic objects situated in the far reaches of the solar system. Saturn, too, with its gigantic rings and gravitational influence, contributes to the general stability of planetary orbits. In addition to the gravitational forces exerted by the planets, the Sun's gravity remains the most fundamental force guiding the trajectories of all objects within the solar system, including Pluto and Neptune. The Sun's pull establishes the general structure of planetary orbits and the overarching stability of the entire solar system.